All right. Hello, everyone. And once again, thanks for joining us. I hope you all are having a great day and ready to hang out with myself, Floyd, and we also have Dr. Prafull Sharma. I hope I said that
Perfect.
right. We will be discussing how to, thank you, how to improve RBI with CUI monitoring. As always, just as all of our webinars, they're very informal and we love engagement. So if you have questions, please feel free to drop them in the chat. We'll try to get to those. And we'll also have a Q&A at the end of this webinar. We also have our first poll up as well, and we will have 3 polls in total. So I'll interrupt at some point and ask you guys to answer the second and third poll. All right, let's get started. So I am Angela Saldivar. I'll be the moderator for this webinar. I'm Antea's Asset Integrity and Risk-Based Inspection Specialist. I have been in asset integrity industry for over 10 years now, working on mechanical integrity projects from the start all the way to run and maintain. I really enjoy helping facilities be compliant. Prafull, would you like to go ahead and introduce yourself and kind of give us a brief story of how you help our industry?
Yeah, wonderful. My name is Prafull Sharma, and CorrosionRADAR is a company based in the UK, Cambridge, and we make monitoring systems for asset integrity, our community, which is corrosion engineers and RBI specialists. We help them make monitoring devices and connect to the RBI. So here we are talking about CUI, corrosion and insulation, which is one of the topics which we are passionate about to solve.
All right, thanks, Prafull. All right, Floyd, go ahead, take the stage. Can you give us a little insight on you and what you do with our industry, and maybe a little insight also on Antea?
Sure. Again, I'm Floyd Baker. I'm the Vice President, Antea Americas. Been in the asset integrity management business for my entire career, 40 years. About half of that career was on the end user side of the business with companies like Lyondell, like Phillips 66, Chevron Phillips, Koch Industries. Then the other half of that's been more around services and technology. And yeah, so happy to be here today. Looking forward to the conversation with Prafull.
Thanks so much. Thanks so much, Floyd. All right, so our agenda today, you are in the right place if you want to learn about technology, sensors for continuous monitoring, corrosion under insulation, so CUI. You want to learn how to leverage CUI data within risk-based inspection, RBI software to achieve predictive corrosion management, Antea's bread and butter. You want to achieve predictive analytics and corrosion prevention at your own plants and facilities. All right, Floyd, I'll let you take off with some terminology.
Yeah, so we'll just start and talk a little bit about RBI because as this concept that Prafull and I are suggesting or presenting today comes to you, it's more or less going to wrap itself to the risk-based inspection methodologies and better understanding the risk, the of course consequence of failure, which there's not a whole lot we can do about the consequence other than shift volumes. But when it comes to the probability of failure, different story. We can actually do things that, perform inspections looking for specific damage mechanisms and either identify one that they're there and which is going to reduce risk because now you know and you can mitigate, or two that they're not there and which also improves risk. So this is a means of not only being predictive in terms of what might be there but also being more prescriptive in terms of determining the conditions that might cause an event to take place. And in this case, that event would be CUI.
Okay, thank you. So what is corrosion under insulation?
Prafull, you want to take that one?
Absolutely. That's a favorite topic I have. So CUI,
Yes.
I mean, there are many over 70 damage mechanisms, types of corrosion, and industry is battling with, and corrosion under insulation comes invariably among the top topics of the asset integrity. So it's basically a corrosion which happens on the outside surface of an asset, which is still hidden inside an insulation. Insulation can be anything like hot insulation, cold insulations, cold type, or any other type of insulations, but anything which is happening outside of an asset but hidden in the insulation falls in this category. There's nothing special on the damage mechanism. It's just that there's a limited understanding, of CUI. Why is it so fast? Why is it so accelerated? and where is it? So in the cost impact of the CUI is huge in the industry, certainly billions and billions of dollars, and a lot of pipe failures, especially in Europe where we sit, are reported due to CUI. So unsolved problems, and there's a huge opportunity to address this CUI problems and manage it better with technology, risk, and monitoring. Floyd.
Excellent, excellent. Next slide. So let's talk about the challenges that we're looking to solve here. We're trying to improve our ability to plan inspections as it relates to CUI. So basically, if you have sensors that can detect the conditions that promote CUI, then you can actually focus your areas, focus your inspections and your maintenance dollars where it creates the most value, where you see those conditions are higher risk for CUI to exist there. So it really helps you focus a whole lot of your maintenance dollars on where it's going to add the most value versus just stripping all installation, or versus using other technologies that maybe not quite as accurate. What do you think, Prafull?
Absolutely, and as you said, that's on the inspection side of things. And when it comes to corrosion management and integrity management, can we be predictive? There's a whole lot of work going on in the industry about predictive tools, but they are based on assumptions as well. So can we be having a predictive corrosion management? And that's a huge opportunity for the industry. CUI is an example of that. We are seeing the initial applications of predictive corrosion management. So which means you're not detecting too late, you're actually proactively managing the risk. So corrosion management have a huge implications of technologies.
Yeah, for me, it's a lot more proactive means for CUI detection versus than the current concepts of actually going out and looking for a needle in a haystack, even when you use technology that's not always very accurate. So yeah, to me, it just makes a whole lot more sense. It's a lot more feasible, a lot more cost effective. It's just a matter of timing of implementation.
One of the things, Floyd, I like what your analogy is, needle in the haystack, right? I mean, it's CUI is a special case. I mean, corrosion is a general case, but CUI can happen unpredictably at unknown locations. And the problem is the asset integrity inspectors and technicians and engineers, they're trying to be Sherlock Holmes. They're trying to find where that is, and in the process, they have to overdo things like removing a whole lot of insulations, do a lot of NDT, right? And most of the times what feedback we hear is CUI is probably at a fraction of the location where they actually inspect. So the challenge and the opportunity is to proactively estimate or guesswork or even data-driven methodology to find where that likely location is going to be, rather than discovering using a Sherlock Holmes method. So you mentioned about needle in the haystack. Sherlock Holmes is my analogy.
Yes, exactly. Agreed. Slide. So we all know that risk-based inspection is more or less a methodology used to where one can actually calculate risk and better understand not only where they should spend their maintenance dollars, but also what they need to do, right? So you're gonna perform the RBI analysis based on a 580, 581 concepts, and you're going to actually calculate the risk, and you're going to calculate that risk looking for a specific damage mechanism. Now, then you can actually create your inspection test plan focused on that specific damage mechanism, whether it's a general thinning, cracking, or whatever the case may be. You can actually focus those maintenance dollars on the specific damage mechanisms that you're looking for. And this is how you mitigate that risk. You actually better understand, one, if it does exist, or two, that it doesn't. Either way it goes, it's an end to that means. Slide. So one of the ways that we like to look at it is through a digital twin. Now, for me, this just becomes so much easier because I'm a really visual person. Prafull, I like to I consume data or consume information so much better looking through visualizations. So the ability to actually look at that digital twin and better understand not only where the risk is, and not only that there is risk in my plant, but where it's at in my plant. and then be able to access all the information associated to that risk right through that digital twin. It's so much easier to consume that data visually than it is, or through visualizations versus tabulations. Tabulations, back in the day when I was younger, that was great. I could sift through Lotus or Excel spreadsheets all day long. I just dated myself, didn't I? Lotus isn't even a thing anymore. So I could sift through them all day long and glean a lot of information from that. But now I just don't have the attention span for it. I read a couple of years ago, read about the lockdown timeframe, COVID timeframe, where I believe it was Microsoft, or it could have been Google, was saying that humans have the attention span of a goldfish. And they say it's about 8 seconds long. So this is why the visualizations tend to capture their attention more so. And they consume the information that they're getting from that visualization so much easier. So accessing this kind of risk information through this digital twin and being able to access all the data associated to that specific asset or assets throughout its life cycle, to me, is most important. Being able to do this in just seconds is what's really key here. Being able to click on an asset or an asset's component or an asset subcomponent and actually be able to drill down on that component or subcomponent or asset and do that in a matter of seconds. We did a case study, a survey with our customers a few years back, and asking some of the questions, where do they find the biggest return on investment through these visualizations, through the 3D models, through smart PNIDs, PFDs, plot plans, even Google Maps for that matter. Actually being able to access that information, and the most valuable return was on TTF, time to find, meaning the time to find the information you're looking for. And in a plant, we normalize the data across all these different size plants, numbers of plants, and so on, and normalize the data to 1,000 assets in a facility. And the time to find feature was $1.8 million per year. So a cost savings of $1.8 million a year in just being able to access information through the visualizations. I thought that was pretty profound. That even applies to anything to do with the CUI surveys. Maybe it's insulation types, maybe it's temperature ranges. All this information at your fingertips.
So Floyd, I just want to make an analogy here. So I would call this digital twin and 3D models and RBI and showing this is more of I would say it's getting into humanization of engineering. That's a direction we are going. Visualization is a human way. I mean, we are not evolved to make tables and look at tables. Yes, we are trained to do that as engineers, but as humans, we are more visual. So the closer we do as a 3D models, even risk, the closer we are to humanization. So that's the direction I would say everybody's going. And I think you, Antea, have done a great job in making boring 2D tables to a 3D visualizations as well. What do you think?
I agree. As a matter of fact, we were the first to introduce 3D models in an asset integrity management platform in 1996. Computers were still relatively new back then, certainly the visualization. So again, seeing that, being a forward-thinking company and seeing this evolution take place, the 3D models was only part of it. 3D models and also 3D point cloud. So digital twinning. But the key here, in my opinion, isn't just the data we capture in the moment of an inspection or a test or a CUI survey, anything like that. It's really about having the edge environment speak back to us, the asset itself speak back to us. This is what really creates the digital twin, because it's actually talking to us now. It's telling us how it feels, what its temperature is, what its pressure is, what flow rates are. Now we get those visualizations begin to speak back to us. And that, to me, is where we really close the loop and bridge that gap between information technology and operational technology.
So if I'm a user of this, say time to find is the metric, but then I will be able to explain this just to my management and my fellow engineers in a much easier way because it's a visual tool, right? So time to explain is another one which I like, personally. Time to explain, time to communicate. Otherwise, I have to communicate through reports, which is again is a boring way.
Yep, agreed.
That's great. We sorry to interrupt, guys. We do have our second poll up. I was on mute earlier, but it is
Okay,
up.
excellent. Next slide. So types of corrosion data captured. We know we always capture our NDT data, so kind of humans as a sensor, if you will. Technicians, inspectors going out in the field and gathering, whether it be ultrasonic thickness data, I don't know, phased array, whatever, radiography, whatever kind of data they're capturing, and bring it into a platform so that you can actually analyze it and manage it. The other parts of that is ensuring that your corrosion probes and coupons programs are all connected also, because this is all corrosion and damage data that you want to be able to monitor in a platform. Lab analysis. I know this sounds a little bit off task for asset integrity, but the process affects metallurgy, right? Process not only the constituents that make it up, but also the pressures and temperatures it runs at. Everything can change the pressure envelope in some way, shape, or form at some level. So also remote sensors. We know we can capture data from remote sensors, either from remote sensors directly or from PI data from data historians, DCS, PLC. All this sensor data is really valuable. Now, here's where it really gets interesting, where you actually connect to this to the corrosion radar platform and actually be able to access that sensor data to better understand and track and monitor the conditions that promote corrosion under insulation right there in your digital twin. This to me is really interesting.
Absolutely, Floyd. And I would make analogies here again. RBI. I think what the parameters which you are showing there are two types mainly. One is the leading indicator, and the other is the lagging indicator parameters.
Mm-hmm.
Lagging indicator is too late, but still useful to capture. It's hard evidence getting into RBI. But leading indicators are also important. So one of the aspects which I will talk about is, example in CUI, we have in API 581, we have like conditions like marine, or is it severe dry climate, is a kind of leading indicator. But what we also do through the remote sensors is an additional parameter like moisture sensors, moisture in the insulation. So that's an example of a leading indicator which does not necessarily lead to corrosion right away, but much in advance it adds to the risk tables. So leading indicator, lagging indicator is a good way to look at these as well. And I like leading indicators because that is much ahead, or much in advance. It can predict the risk.
Yeah, it's much easier to predict and plan in order to mitigate, instead of the lagging indicators, of course, where you've already got a problem and you're having to deal with that.
Yeah.
Slide.
All right, so now we talked about CUI, we talked about RBI, we also talked about digital twin and the opportunities lying ahead, humanization, Sherlock Holmes. How do we do this? So how do we achieve continuous CUI monitoring? Now we have seen CUI to be inspection oriented, lagging indicators based inspection oriented, visual inspections. But now is a technology which I'm talking about, which monitors the parameters, few parameters, which are leading indicator parameters for CUI. So jump into technology. So next slide, please. So in the CUI space, the core problem is when and where is risk going to happen much in advance. So suppose CUI has not yet happened. Probably these are newish pipelines or older pipelines, not even pipelines, some assets, pressure vessels. The core question is where it's going to happen. So because of that, CorrosionRADAR have invented a technology which is a long-range sensor technology. So it gets installed. What you see on the screen is the orange colors are basically wire type sensors which are about 100 meters long at a time, connects to a data logger with a blue box here, and transmits the data wirelessly to softwares. It can be any software, data visualizations, and RBI softwares, Antea. So in this case, the sensors are interesting in the sense the sensors are covering a wider range, long range, and there are two types of sensors, moisture sensor and corrosion sensors. And moisture sensor is a leading indicator of finding out where the dry environment is, where the wet environment is. So that earlier we talked about needle in the haystack. So this is finding the needle through sensors. without Sherlock Holmes there. So that's a moisture sensor, and the corrosion sensor is an augmentation of that because moisture does not necessarily lead to corrosion. So corrosion sensor is the longest coupon in the world we have here, like a wire, and it locates where the corrosivity is. Is the corrosivity medium, high, or low, or very high? That level. So this is about when and where CUI is likely to happen, and then this all these data is combined and analyzed and put it into risk tables and connects to the RBI matrices. So that's the language. Risk is the language, but the source of the data is moisture and corrosivity sensors. This device is widely available, 8x rated or explosion proof rated, and I'll talk about some of the case studies. Next slide, please.
Next slide.
So here's a video of example of a digital twin aspects of how this affects. Obviously, the sensors can be used even without digital twins, but the enhancement is with digital twins. So this is an example of a tank. The sensors are both corrosion and moisture sensors are wrapped around, and they're sampling a wider area rather than a spot, and the data gets transmitted. And here you see that key locations are identified where the risk, in this case, is medium. So it's really localizing specific spots. In this case, you need not create a scaffolding. You can just do rope access, save the cost, and really inspect where to be done. Now, this is another example where it's a high tower, say 25, 30, 40 meters high, and normally scaffolding are needed to inspect the whole lot. But if we can pinpoint using sensors where the greens are and where the yellows are or reds are, then we can be targeted in our inspections. We can be targeted in our scaffolding. In fact, we need not do scaffolding. We can do rope access. And that's on the scoping side, but also time-wise, if everything is green, then skip the inspection, or defer the inspection if there's a need. So it helps in the decision-making aspects of that. I think the video is stopped. If you can see if we can play it again.
Stopped.
All right, so it's working. Further on, there are, for example, where the immediate threats are, nozzles, protrusions, those are the spots. Now the sensors can be routed through those, and if we know in advance that okay, those are the risky locations, others are green, others are yellow, those can be prioritized rather than the whole asset. So save cost savings there, and safety as well. Complex geometries like these, very difficult to categorize them as to, hey, is it a pressure vessel, is it a pipelines, what kind of methodology we have to apply. So we apply sensors in a complex fashion. It is designed that way, and once the sensor data is transmitted, it really tells when and where it's likely risk is high. So in this case, top and bottom. So, but it can be anywhere as well. Another example is a heat exchanger or a pressure vessel. So in this case, the nozzles are a priority inspection locations in the risk tables. But if the sensors are routed and it tells us that no, some of the locations are fine, but some of the locations are actually higher risk, this is about higher resolution of risk. Normally this whole tank or vessel will be one risk, but now we are actually giving a high definition of risk using sensors here. So you see only two locations were identified risk, so other locations can be skipped with the inspections. So yeah, next slide. So that's the power of digital twin and monitoring technologies. There are these monitoring CUI monitoring technique have been deployed globally in different applications. So you see on the screen what kind of applications. So there are dryers, deethanizers, which are very prone to CUI, the columns and pipelines, critical pipelines, green fields, brown fields, as well as the storage tanks you see there. One of the key good applications are cold assets and cryogenic assets, which cannot be inspected in live conditions. So we need to understand the risk of those in live conditions, because you cannot inspect them. They form ice if you open up the insulation. So that's one of the primary application as well. So yeah, various applications of different kinds globally. Floyd, do you have any comment on the applications?
Yeah, no, I agree. You can actually spread it across many different types of processes. It's just a matter of when you apply it. And again, you mentioned cryo services, and also there's something that happens. Implementation would be during an outage or during new construction. Really, greenfield is the best place to install. But even when you're doing a CUI survey and you're stripping a lot of insulation anyway, the opportunity is there to go ahead and install the sensors. Yeah, that's my suggestion.
One of the other applications is the T&I, the turnarounds planning. So you talked about cryo services or cold duty services, or even intermittent thermal cycles operations. Some of them can only be inspected during a turnaround because it needs an equipment shutdown.
Yeah.
But if you know in proactively that this equipment is fine, there's no threat, there's no evidence of water ingress or corrosivity conditions inside, then it can be kept outside of the turnarounds. So turnaround can be optimized. The other way of looking at it is many times in the turnarounds we find CUI unpredictably, and then the turnaround becomes more extended. Now this is about managing the risk of turnaround extension as well, to know proactively when and where to inspect.
Much better to know in advance than it is to get in the middle of a turnaround and then find you've got not only you got long lead materials in some cases, but then you got overtime. You've got everything is at premium at that point, and you're extending your downtime, which means you've got lost opportunity, meaning the opportunity to be up and running and making product. Yeah, never a good situation. Always better to know in advance, and with tools like this to be able to know in advance and plan for it before you oil out.
Thank you. Next slide, please. So let's get into some of the case studies with some of the main users of this technology. So in this case, in the US major, in this case, a pipeline is being deployed with monitoring sensors with battery-powered data logger. The white box corrosion-radar box you see is a battery-powered device, and it connects to the sensor, which you see on the left-hand side. So in this case, a long pipeline, so it's a critical pipeline, single point of failure pipeline. So this chevron deployed there, and the goal is to have a leading indicator of CUI rather than lagging indicator. Next slide, please.
Again, we do have our third poll up,
right.
So go ahead and find that in the poll section. All right.
Another example is of a dryer or dehydrator, which is more of a combo of cold duty insulations as well as thermal cycles. So this dryer goes from -15 degrees Celsius to 180 degrees Celsius. It's a poison of CUI. It's a recipe for CUI, and if it's ignored, then it's not a good situation for CUI. Now, this dryer will be inspected only during a shutdown, so you can't really inspect it in live conditions, and that's makes it difficult to actually, you often have to do a mini shutdown just to inspect these kind of assets. So CUI monitoring is a good case here. Obviously, there's a risk and consequence of failure and probability of failure. And what we found out here is the asset owner reduces the risk officially in the RBI tables when they use monitoring, because they know more about the asset. The uncertainties of knowing what is the water ingress and the humidity ingress in this asset is less. So there's a huge cost savings in these cases. Have you seen any similar threats in RBI, Floyd?
Yeah, I have not. That coupled with the structured data data captured by using mobile applications, so that one can actually capture things like drop-down menus, maybe it's tick boxes, but you can actually trend and start to see where insulation damage, where an inspector has documented insulation damages. You couple that with the kind of data you're capturing here, and it really helps you hone in on where you need to be focusing on, in my opinion.
Thank you. And another aspect of pressure vessels inspections is, many times regulatory bodies gets involved and enforce a time-based inspection. And then now more regulatory bodies, globally, especially in Europe, they are moving towards more risk-based inspections. But again, in risk-based inspection, you have to inspect these often certain years. Now, if we can justify that, hey, we are using monitoring, so the risk is lower, so the inspection will be longer duration. That's some of our customers are going in that direction. That benefit of that, more data-driven inspections.
Yeah, to me, it automatically takes into account things that you would not know until you actually perform the inspection at this point. So if you start talking about your inspection effectiveness, to me, it's a much higher value because you've actually got data to support either one, the conditions do exist that CUI could be there, or two, they don't exist. If there's no air, there's no fire, right? Same here. Same in this situation. So to me, it should. I mean, it does support a much higher inspection effectiveness and helps hone in on that probability component of that equation.
Sure. Thanks. Next slide, please, Angela. A good case study here, which is among my favorites as well. You know, the top. This is because this is a very high production column, and I was personally involved in talking to the end user here. They came with a lot of pain that this asset is 40 years old, and this is in Netherlands, and they had to do life extension of that. So they were managing risk, but this is beyond risk. They know the risk. This is high consequence and high risk. And they have to do inspection every few years just because it's a life extension program. They have to do 6 every 5 years or 6 years. They know there's a condition of CUI. Now, what they came up with that, hey, we know we have to inspect this every 6 years, but it creates a scaffolding, and you know, we have to inspect key locations like rings of support rings, which are prone to CUI, and nozzles. But can we be smarter? Can we inspect it only when needed? So that's where this monitoring came in, and the sensors which you see on the screen, which is helical fashion, it was installed in key locations. And this has been a few years, and they have actually detected that CUI conditions are not there in most of this asset. There's insulation is perfect, but at a certain location, they found that water ingress is happening and CUI conditions are getting developed. So that location on top is being publicized. This company and the end users have publicized that we have detected using technology, and now we are doing rope access based inspection only on that particular location. So we are managing the risk in a much better way. So in that sense, if you see the RBI table there, they're saying that we reduce the risk because now we know much better where things are going to be. So officially reduce the risk, extend the inspection intervals, and save the money. So a very good use case of a production column.
Yeah, I agree. That's a really good example right there. That's that's a perfect example, a case study of value add for utilizing a more proactive, predictive means in the sensors and the sensor data.
Next slide. All right.
So I guess we kind of talked about this a little bit before a moment ago. You know, how CUI data, sensor data, can enhance your RBI. It's really pretty clear to me. You know, if you know the environment, it's a known condition. It's either a known condition or it's known that it does not exist. So to me, it enhances your RBI. It's going to improve your inspection effectiveness component of the equation. It's going to improve the quality of the inspection because, again, it's more predictive versus following up later after finding the damage during a turnaround or even while you're up and running. Bottom line is, you know in advance whether the conditions exist or not. So to me, it has a direct impact on your RBI output. Next slide, please. So how to integrate your CUI monitoring with RBI. So this is basically what we're saying here is being more predictive about your inspection and testing, specifically CUI surveys, CUI inspections, being able to better understand where those conditions might exist. Go ahead and turn the next slide, please. Where those conditions might exist, and being able to focus your energy, your resources directly in those areas. Go straight to them and either remove insulation or use profile radiography, who knows, using different technology to actually detect said CUI. So when you actually use this asset integrity management platform as a hub for all these data inputs, including the sensor data, you're actually creating a bridge between what we call your IT, information technology, well, that's your legacy systems like SAP, Maximo, Upkeep, any of your ERP, EAM, or CMMSs, and then connecting that to the OT world, your PI data or data historian, DCS, PLC, or SCADA, being able to be the bridge in the middle and collect all this sensor data to where you can actually analyze it and make decisions in a single place. Yeah, it's basically how you create the digital twin. Next slide, please. This slide here covers the same information. It's really about connecting your IT to your OT, but it's also about bringing, as I mentioned a while ago, humans as a center is an example. Prafull, I call them humans as a sensor. Really, we're all collecting data at some point, right? You got operators out there doing operator rounds, and they're documenting things that are happening. You got maintenance technicians out performing maintenance on these assets, and they're documenting things. We also had non-destructive testing technicians. We've got inspectors. Everybody's collecting data. So really, we're acting as a sensor. And in many cases, we're using one of the 4 dimensions of mobility, whether it be a smartphone, a tablet, or wearable technology. Either way it goes, we're sensors collecting data, but also pulling in all that non-destructive data straight from the devices themselves. So really, it just closes a loop on every bit of data that's associated to any given asset throughout its life cycle in a facility, and bringing it into one space so that one might take actionable decisions.
I like
Next
your
slide.
analogy of human as a sensor, because we have the best sensor in the world: eyes, ears, and the brain.
Yeah.
Estimations, but there are limitations. We can't see under the insulation, for example.
Yep.
And that's where we have to
right.
augment. Yeah, that's where we have to augment with all these sensor technologies, X-rays, for example, pulse rate currents, and monitoring technologies like sensors. Where our limits, human limits are, can we augment with technology and use a better decision making?
Yep, you're exactly right. It takes both. It takes humans for a lot of decision making, but also it takes the data itself, the sensor data, to actually be able to give the humans something to analyze. And then also some of the future things we're working on here are adding some AI features and artificial intelligence features and machine learning features, along with the analytics aspect of it.
Yeah.
Next slide. So we talked about digital twins a while ago. We're calling this digital twin 2.0 because we're actually introducing information or data that has never been introduced into a digital twin. We've talked here a few weeks ago about the another partnership with Clean Connect, where we're bringing computer vision into the platform using optical gas imaging technology to actually not only detect but identify and quantify emissions, fugitive emissions in the plant. Now we're talking about bringing in CUI sensor data to actually be able to understand where CUI is highest risk in the plant based on that sensor data and the analytics associated to it. So doing things that most digital twins really don't do. We're calling it digital twin 2.0.
That's a great term, digital twin 2.0. And in many ways, Floyd, this is again, in the nature, there are so many examples. So this is industrial world, but in the medical world, a lot of these things are getting used. Doctors use a lot of tools, X-ray, ultrasonic, to understand the human body, and then they use a lot of analytics tools, digital tools, right? But the key difference there is, compared to human body and the industrial world, that the industrial world does not have a nervous system which tells them that hey, there's a problem, right? To go to a doctor altogether. In the industrial world, sensors are needed as a nervous system to tell that hey, there's likely a problem. We don't know how severe the problem is. Just attend to it. So that's where the opportunity here is in the CUI monitoring, connecting it to digital twin, and make it more closer to a kind of natural world which we all exist in.
Yeah, that's exactly right. As a matter of fact, a lot of the technologies that we use today come from the medical industry and vice versa. But one point to make here is that these sensors make it possible for, as I mentioned a while ago, for the asset to actually speak to us. A doctor can speak to a human. Humans can respond and say, hey, it hurts when I do this. And the doctor says, don't do that. Bottom line is that you can actually talk to the human and determine, what's going on, and help to better focus in on what the real issue is, what the pain is, in order to make a diagnosis and, of course, prescribe something to fix it. Well, using sensors, we're able to do the same thing with the asset itself, with the equipment themselves. It can actually speak back to us and tell us what condition it's in, tell us what its temperatures, pressures, moisture, whatever the case may be, so that we can better understand how we can help it have a longer lasting life, improve its life cycle.
Learn from the nature.
Next one. So we talked a little bit about humans as a sensor a moment ago. So we're going to talk a little bit about the driver for remote access to data. So accessing real-time data nowadays, you can do from, we can do from our mobile phones, from our tablets. All this information can be connected using connected technology to actually access the information and help make decisions no matter where you are, whether you're at the plant, whether you're in downtown Houston at your corporate office, it really doesn't matter. One thing you can think about is connecting things like with using QR codes. Using QR codes, you can actually scan the QR code and access all the information associated to that specific asset. And at the same time, if you're integrated to your CR data, to your corrosion radar data, you can actually access the CUI information. Now, this is really huge when you're planning work, when you're actually planning, doing activities in a plant, because you don't necessarily have to be there in order to plan it. Here, you can actually visualize the assets and actually do planning, like planning for scaffolding, where you see a high potential for the CUI to exist. You want to be able to plan for scaffolding. You want to be able to plan for maybe staging equipment or staging materials, new installation materials, what have you, or maybe it's a rope access plan. But all this can be done right there through a digital twin, and could even be done from your smartphone or tablet.
I think one of the aspects here is time to respond or time to gain information here, because many of the inspectors or many of the engineers, they have to visit plant, and if they have some information missing, they have to go back to their offices. That loop is time consuming, right?
It is.
I am right now, Floyd, I'm right now in the Middle East, visiting some plants, and the asset integrity engineers have a hard time in summers going out, and coming back. The plants are huge, and the weather is not helpful, right? So if you can save them time, they're happy. So I think mobile technology, getting information right at the asset level when they're visiting the site rather than going back and forth between offices, is a huge advantage.
Yeah, it actually connects to the digital transformation journey. And note, I did say journey. Digital transformation is not an event, it's a journey. And I can remember back in the day when I was just an inspector, contract inspector out at Exxon, and having to go all over the place just to find all the data you need to do something like, I don't know, a re-rate or maybe a repair. Some of the data would be in the maintenance shop, some of it would be in operations, some would be over in engineering, and it just take you days to come up with all this information. However, through that journey, most folks have come to a point where they're at least digitized. Not everybody, but most are at least digitized. That means their data or their documentation is in digital format in a shared drive someplace. Now, in most cases, there's still a data silo there because not everybody has access to that shared drive, right? So to me, creating this bridge between the IT and the OT is ideal in terms of time to find, because all of the information associated to any given asset throughout its entire life cycle is right there in that same space for anybody to access. Of course, permissions have to be set. Some people can actually influence the data. Some people can actually can only read the data. So, but still, it's valuable to everyone. And remember, I mentioned that $1.8 million per year in savings for an example of a facility with 1,000 fixed assets, meaning just pressure vessels, exchangers, towers, not considering piping, just 1,000 assets, $1.8 million a year. That's huge. That's huge to drop onto your bottom line at the end of the year.
So Floyd, so some of the attendees might be thinking that, these devices, many of the companies have policies. Obviously, we're dealing with hazardous locations, and the devices may not be, allowed there. So are there ATEX or class 1, Div 1, Div 2 rated devices available?
So, you can use specialized tools, but you also have cases, these certified certified cases that you can use that are acceptable as well. One of the companies, I'll just off the top of my head, is Joy Factor, that makes these things. You can actually just put your smartphone in if it's an Android or an iPhone. Same for tablets, and that makes them where you can actually take them out of the facilities. It's becoming a lot more commonplace nowadays, simply because everybody's collecting data through mobile apps nowadays.
Yeah, thanks.
Next slide.
Lloyd, I was going to touch base on the intrinsically safe cases.
I mean,
Yeah,
there are even devices available now which are inherently intrinsically safe, the mobile devices which are being used as well. So technology have gone leaps and bounds for our engineers to use.
Yep.
So we do have quite a bit of questions, and if we click on the view questions, you can see we got about 20 questions so far, so we can start going through some of those questions. Yes, lots of engagement. So the first one, what are the life of and warranty of the coal sensors?
Right, the CUI sensors. So CUI sensors, they are normally between 15 and 20 years life, but inherently we have a moisture sensor and corrosion sensors. Corrosion sensors are like it's a coupon. It's the longest coupon in the world. If there's no corrosive environment, it should last 15 to 20 years. But if there's a corrosive environment, the coupon will corrode at a particular spot. So that, but the other spots, other locations of the sensor will continue to work as it is if there's a dry environment, and multiple spots can be detected. And then if it needs to be refurbished, a part of the sensor can be changed and removed. So say 1 meter length sensor can be removed and reconnected. So yeah, that's the answer.
So one thing you mentioned too, I see another question here around that intrinsically safe is, yeah, there's a lot of plants that won't allow you to use your smartphone or tablet in the plant or in the unit. In many cases, that's changing. That's evolving over time here. But also you have to consider there's also, as I mentioned, there's actual cases that make it intrinsically safe and where you can actually carry it anywhere. So that's a response to that question there with regard to ignition sources and mobiles in the plant.
Yeah.
Okay. We also have another question. How specifically can we know this is a CUI and does not interfere with other types?
Yeah. So I think in the sensor side of things, if it is so there are two sensors. One is water. Water is water. I mean, detects water. And the second sensor is corrosion sensor, which is corrosivity. So this gets installed under the insulation. Now it doesn't have to be a kind of specialized condition. It basically it says about corrosivity, whether there is a corrosivity in that location or not. Now it does not mean that there's a CUI existing right now, because there may be coatings. It's all about knowing the risk. So it's not about distinguishing different corrosion mechanisms here. It's about knowing that there is a corrosive condition getting developed there at a particular location under the insulation, and it's worth looking at it from the risk point of view. So that's how we see it. The sensors are basically corrosivity sensors and moisture sensors.
Okay, thank you. Are the sensors hardwired or remote sensors? Does this require the vessel to be entirely stripped for install? Can these be added to existing assets?
Yeah, I mean, the sensors, they are retrofitted in brownfield applications. Obviously, insulation needs to be removed when there is a existing inspection going on. Greenfield is a different question. It is part of the design in many cases. Many of our end users are using in the design. But the brownfield application, it's when the insulations can be removed. For example, cold duty insulations are removed during inspections, and it need not be done for the whole asset. It can be done only on critical locations which are prone to CUI, and the end user wants to know whether the assumption is there's a prone to CUI, but is it really a right assumption? Can we skip the inspection? So that location can be covered, critical pipelines can be covered, and the installation is done usually removing the insulation in brownfield during a turnaround or during a inspection interval.
Okay, and then the technology can be adapted for all sorts of insulation, irrespective of density.
I guess this is a sensor question, and I believe RBI question will be with you anyway, Floyd. So sensor point of view, there's no limitation on the type of insulation here. It can be mineral wool, glass wool, and it can be foam glass, it can be cryogel, silicate. Insulation doesn't matter. What matters is technology works in all the cases. Water is detected using moisture sensor. Corrosive conditions are detected using corrosion sensor. It's more about where to apply and when to apply. the limitation of insulation is not limited. So I think I guess the question was also on the technology. So I don't know whether RBI or risk. There's a question on that.
No, you covered it. I think the main thing to understand is that the actual sensors connect are installed in contact with the substrate. So the insulation is on the outside of that. It doesn't matter what kind of insulation it is.
Yeah, yeah. And just to elaborate on that, the sensors need not be in contact. There's no technical reason why the sensor needs to be in contact with anything like even a pipe or metal surface. They are basically independent sensors. They're kept on the table. That even that works. You put it on a table, put water, it detects water. So that's the core. And if it is, in many cases, the sensors were installed in an end user case where it was not in direct contact with the asset, but close enough, but after a layer of insulations, because the end user said, okay, the temperature is too high. We don't want, the sensor temperature limit was 300, but the asset temperature was about more than that. So you put, okay, there's a layer of insulation in between the sensor and the asset. So just to protect the temperature to the sensor. So that's the technical advantage there.
Yep.
Okay, we're getting a flood of questions.
So a lot of good questions, Floyd. Looks like we have covered a good ground. I confused a lot of people, but that's a good confusion. Good problem to have.
Yeah. Yeah, I think also if there's any questions that we don't get to, we'll certainly respond to them after the webinar. We'll respond via email. So the difference in this technology, there's one here that talks about long-range guided wave ultrasonics. This is not ultrasonics. This is actually sensors that are measuring for corrosivity, or sensors that are measuring for moisture, these sorts of things. Long-range guided wave ultrasonics is specific to send a longitudinal torsional wave down the pipe in order to look for anomalies in that distance, in that length of the pipe. So two different technologies.
Yeah. Just my addition to that, I'm a fan of ultrasonic guided wave as well. But the limitation, it's an inspection technique. It's a lagging indicator type methodology.
Yeah.
Obviously, it is needed. We are not eliminating that by adding monitoring technologies, because inspection is still needed. We're just managing the risk much better. That's how it is. It's all the tools are to be used to manage the risk better. So in this case, as you rightly said, guided wave ultrasonic is inspection technique, but through monitoring, we can tell when and where to inspect and do the guided monitoring rather than doing guided wave ultrasonic everywhere, because it's also expensive method to inspect as well. There are limitations as well. And what we use, it's a similar philosophy. The monitoring is in the form of a wire. We don't use pipe as a waveguide, but we use sensor as a waveguide. And then sensors are embedded, but we use microwaves, electromagnetic. But the similarity is it's both uses time of flight. You send a pulse, and then wherever the defect is, the pulse gets reflected. So similar philosophy, but slightly different philosophy as well.
There is a question here. Is there any possibility data error from the sensor? If yes, what will be the variation range? And then also, he asked, some insulation have heat trace. Is there any possible conflict or limitation for obtaining the data and able to send the signal from the sensor?
All right, so I'll answer the second question first, because the first question I did not really get it. So second question first. So heat tracers,
okay.
we do a lot of questions on this. So the sensor temperatures are from -190 degrees Celsius to 300 degrees Celsius. I say 3 degrees Celsius, sorry, Floyd, because I'm based in the Europe, right? So from the UK,
right.
Fahrenheit, I have to do a lot of mental math to do Fahrenheit. So minus 190 degrees Celsius to 300 degrees Celsius. Now, if the heat tracers are above 300 degrees Celsius, then ideally we have to put a layout where the sensors does not touch the heat tracers. If they have to cross over, then we put a small layer of insulation so that they don't contact between them. Now, if it is below, the heat tracers themselves are below 300 degrees Celsius, no problem. The sensor can be in direct contact with that. So, Angela, can you repeat the first question, please, on this?
Is there any possibilities there's data error from the sensors? And if yes, is there a variation range for those data errors?
Yeah, I mean, it's the other way to say that is probably false calls or unknown spurious signals. Um, it's a good debate in the industry as to what we can live with. Now, in kind of sensors and monitoring technologies always battle this. It's a battle between the signal to noise ratio. What is a good signal? What is a false call? In one of the cases, we had an issue where unknowingly one of the technicians during refurbishments of the insulations, they cut the sensor, they damaged the sensor. Now that can be regarded as a false call, that sensor detected something. We don't know quite yet what it detected, but it was a very sudden event. Suddenly it detected that there's some signal. Now investigations led to the conclusions that okay, actually that was damaged by mistake. So this is an example of false calls. It does happen. I won't say it's a 0%. So there's a certain percentage, but not a whole lot. In another example, we noticed that the end user, the asset owner, the integrity people assumed a certain temperature range of the asset, say about maximum 250 degrees Celsius during operations. But then there was a signal came in that hey, something was detected and it is unusual, when the experts looked at it and from the signals, and then we realized that no, the sensor have been damaged and probably likely due to thermals. So the temperature went above the temperature limits which the design engineers or the asset integrity engineers knew of. Probably it went above 300 degrees Celsius, 350. So the sensors got damaged. So these are the examples where off limits, unknown cases, the signals can be spurious, and so experts have to look at it in those cases.
Thank you very much. So I think that's all the time that we have today. But if you'd like to learn more, you can go to www.antea.tech for more resources. We also have some really great news. We will be having another Asset Integrity Summit, and it will be in Louisiana this time. So this will be our second. Please keep your eye out for the invite. We had such a great time on our first one, and we'd really like to offer it again. This will be a great educational event for our industry. If you would personally like to receive more information from myself, Prafull, and Floyd, please send us a direct message on LinkedIn. We'd love to hear from you. Thanks, everyone. Thanks, guys, for all of y'all's great information and feedback that y'all have given. We're so happy you could join us, and we'll see you next time.
Thank you, Angela.
Thank you.
And Prafull, you travel safe, and we'll see you soon.
Yeah, I have a flight to catch soon. So
Yes.
thank you. And
Yes.
it was a great conversation, Floyd. And as always, enjoy the conversations. And all these new techniques are actually bringing a change in the industry. So we represent the industry together and the community of corrosion and asset integrity engineers. So a great conversation with you, as always.
Thank you so much, Prafull. I've really enjoyed
Thank you
talking
so
with you as well.
much.
We'll talk again soon.
Thank you, Angela.
Take care.
Take care.
All right.
Bye-bye.